Hello, Viva Cunliffe here, CEO Reduction Tech. Today we're going to talk about aerosols and the hydroxyl. So there is a very strong relationship between these two that is not highly published in the peer-reviewed literature. So I'm going to provide what I've picked up from the peer-reviewed literature here and add a few thoughts and understandings. Not much, but I think you'll understand why aerosols do inundate hydroxyl. So I think the aerosol removal process abuses the hydroxyl system and the earth system in about 4 different ways. Aerosols deplete moisture, especially hydrophobic particulate matter. It matters whether the base particulate is friendly to water, repelling water, or it is neutral. It makes a difference in how that is eventually removed from the atmosphere. Hydrophobic particulate matter is often used in artificial spraying for weather modification, and so that particulate persists in the atmosphere. It's the theory behind doing solar radiation management particulate dispersal, where the longer it stays up there, the better, the more resistant it is to hydroxyl. So that is a damaging aspect to the hydroxyl radical levels. Also, the aerosols dilute OH, lowering its relative abundance, which means that you fill up the right-hand bucket more than what was in the left-hand bucket, and relatively speaking, the left-hand bucket is now relatively less abundant to that amount. So that's the simple concept of relative abundance. Aerosols directly deplete hydroxyl as hydroxyl attaches. So a large particulate can have more than one molecule interacting with more than one hydroxyl. And this goes all the way down to the molecular level. The hydroxyl doesn't know what it's coming up against in the atmosphere. It's just looking to steal an electron and try and stabilize its own molecule. So you can get a couple of them, 3 of them, maybe more attaching to an aerosol, which is a great thing to have happen because that weighs the aerosol down, and then it's removed either through dry gravity process of being deposited on ground, or it gets caught up in the weather system. So it's very important to know that particulate matter is depleting in that way. Aerosols also confound the record levels of other constituents. Okay, they're in there mixing up with everything else that's in there mixing up. It's making a mixed up mess. So this requires more hydroxyl for wet and dry removal. And we have come out saying that it is currently inundated because of this situation. It's a fully confounded atmosphere. So I have a little graphic that I'm going to show here in animation. I've got aluminum oxide on the screen. Now, the aluminum is repellent to water. So when water comes in and interacts with this molecule, it prefers to interact on one side of the molecule, which is the oxygen facing side of it, so that because oxygen is more soluble and hydroscopic to water. Okay, so we have hydroxyl coming in. It's attaching, looking for an electron. It attaches on. The electron is there holding it together electromagnetically. We have water around now coming in, and an electron is also involved. And then we have a wetting aluminum oxide molecule is what you're looking at. Okay, so, and it'll build up on one side of the particle, probably initially at the very microscopic nano level. And then this is a lot heavier. And once they start coalescing together, this is how you get rain. But this is how hydroxyl is lost to the aerosol. So also a parallel is happening with the forever chemicals. The same principles apply for removal of any large molecule in the atmosphere that is not being oxidized or hydrolyzed by the hydroxyl. So you have electron stealing by hydroxyl, which drives the process of the molecule being engulfed into a droplet or weighted down. Same principle. These chemicals will end up in the soils after spending decades of time in animals and plants. They likely are affecting our biodiversity. It looks like this is a very powerful cancer vector. So anyway, the hydroxyl can attach to some of them. It's not getting all of them. If the forever chemicals are quite neutral, it can go after the orbitals in the molecules and attach. So an increase in hydroxyl means an increase in forever chemicals removal, but we also know that we can provide us the most electronegative oxidant is the doubly ionized oxygen, which is oxygen with a -2 charge. So it is missing 2 electrons, which is very, very good match to all of the halogens that are in the chloride, fluoride, bromide group that is very difficult to remove from the Earth system. So again, aerosol forcing, same thing. A molecule, hydroxyl attaches, electron is trying to stabilize, electrons are trying to stabilize. The water becomes accessible to the particle and they come together and they form a wet droplet. This is how hydroxyl basically makes a cloud condensation nuclei enter water and cause the formation of droplets for rain. So, of course, with the forever chemicals, I just like to close up by saying that we really don't want to drink rainwater or freshwater fish probably for quite a while, unless you have a home system where you can deal with the forever chemicals. And what you're going to need is some kind of oxidant that is stronger than the electronegativity of most of the halide group. So that is probably going to be with us for a few decades, unfortunately, until it gets eventually taken down into the soils and out of our living area. So here we are. We can all be heroes and bring down the hammer on climate and biodiversity collapse with hydroxyl dispersal, which is what this short presentation is supportive of. And the goal of our company is to move humanity past the climate disaster by 2021. So I'd like to thank you for your time today and wish you a good day today.